Hey, so we are doing homework number 11, problem number 1. Let x of t be a WSS real random process whose autocorrelation function is periodic with fundamental period t. Show in this case that the least mean square error linear estimate of the value of a sample function at a time which is an integral number of periods away from an observation instant is equal to the observed value. That is, show x caret of t plus k big T equals to x of t for any t, comma k, an integer. And there's we're given a hint, and so let's look at what we know. We're given that x of t is a WSS real random process. The order correlation is periodic, so r of tau plus rt is equal to r of tau. And so therefore we want to prove that x caret of t plus kt equals to x of t for any t, comma k, an integer. Okay, so to look at this, we want to examine the error, and that is the expected value of the quantity of x of t plus kt minus x caret of t plus kt squared, and we want to make sure that error is minimized in order to find what we are looking for. And since x caret is a linear approximation of x of t, we pretty much can show that x caret of t plus kt is equal to ax of t plus b. And so to find the least error, we take derivative of e, the error, with respect to a and b. So with respect to b, we're going to start with b over here. So dE dB equals to d error over dB. We want to set it equal to 0 to minimize error. And so we worked it out. The expected value of -2 times the quantity of x of t plus kt minus a x of t plus b, and we can take this -2 out and then separate these two. Then when you take the -2 out, it equals to 0 because you just divide the other side by 0, and then you're stuck with just this part. So we just separate the e out for both parts, and then we also have the -b over there. And what we can do is set the b equal to eta values. They're not constant, they're just eta values. And that essentially equals to b equal to eta eta subscript x minus a eta subscript x. And so once we find the b, we want to find our a value, and we have dE dA, d error over dA, again equaling to 0. Same thing we did over here. Pull the 2 out, it equals to 0, so you get rid of it, take the expected value of it. But this time you actually sub in, for b, you sub in this value, and that's what we did here, as you can see. And so we further simplify this equation by divvying out the expected value. So we can take out this, take the e of this, take the e of this, take the e of this, and take the e of this. Eventually we arrive to an area where the expected value of x of t times x of t plus kt minus a of times the expected value of x of t squared minus eta squared plus a eta squared. Okay, so we factor out the a over here, and this equals to r of kt, and we basically have r of kt minus n squared of this over this value equaling to a if you just move around the values, and that equals, this essentially equals to the covariance of kt over I forgot what this Greek symbol was, but this one. Yes. And then after this, what do we do? What do we do? Oh, Yes, since r of tau is equal to r of tau plus kt, because it's periodic, it also equals to r of 0, so we substitute this into the equation for a. So we substitute r of 0 minus n squared of t, as you see over here, expected value of x of t squared minus eta x of squared, and we get, and this top part actually equals to the bottom part, essentially this equals to 1, and so we substitute this back into our original equation over here. This a is 1, we showed it over here, and n of x, eta x minus eta x is 0, covariance of kt is equal to 1, so therefore this part is equal to 1, and therefore x hat of t plus kt equals to x of t, and that is problem number 1.